we go into an organization to have conversation about using teleport over there, it's very common to feel the animosity that exists in the room between engineering and security. Because people feel that security gets in the way, prevents them from being productive. So let's just be nice to each other and not do that, and design systems to be trustworthy and nice to use.
Welcome to Access Control, a podcast providing practical security advice from people who've been there. Each episode will interview a leader in their field and learn best practices and practical tips for securing your org. This is a special episode recorded in person at Teleport Connect 2023. We'll be publishing a video of this conversation at Teleport Connect Virtual Replay on February 8th, 2024. Or if you're listening after the release, you can always catch a replay on Teleport's YouTube channel. For this episode, I'll be chatting with Ev Kontsevoy, CEO of Teleport. Teleport is an open infrastructure access platform, started in 2015, and Ev also holds the number 2 contributions on GitHub. Ev is a serial entrepreneur and was co-founder of Mailgun, which successfully sold to Rackspace. Prior to Mailgun, Ev has held a variety of engineering roles. Ev also co-authored the 2023 O'Reilly book, Identity Native Infrastructure Access, and we're covering lots of those topics today. So Ev, welcome. To kick things off, I'm going to deep dive into your book. Can you tell me about the pillars of access?
So at the end of the day, I will say that I just don't like the word security. I think it's a little bit kind of disconnected from the actual benefit we want to get from computers. So it all comes down to, are computers trustworthy or not? Because if they're not trustworthy, then they're useless. So I believe that we're in the business of actually delivering trust to computing. So you want your computing system to be trustworthy. So maybe I'm reformatting your question by saying, what are the kind of pillars of trustworthiness? And that's where that CIA triad comes from. So confidentiality, integrity, and availability. So if you have those 3 things and they're true and they're not getting violated, so that means your system is trustworthy. Another way of looking at it, so when you say, okay, what do we need to do to build a trustworthy system? So this is what I talked about earlier. So one of the components is that you do need to have an access control system. Because access control is basically about enforcing policy when subjects and objects interact with each other. So subjects, that's applications and people. So they all need to be treated equally. It's really, really important. And objects, that's your data. So every time people and applications interact with data, you need to enforce policy. So that's what access is. And now we could talk about, so what are the pillars of access, actually? So from a technical perspective, there are kind of 4 components that access consists of. That's authentication. People need to log in. That's the process of issuing an ID. So the importance of having identities is really, really important. Also, everything that I'm talking about equally applies to humans, to applications, and also to hardware, which means that applications need to log in, hardware needs to log in. When a server comes online, it actually needs to kind of log in and prove that I am actually a legit server. I'm not a honeypot. And the same thing for humans. So that's authentication. So once everyone is authenticated, and now everyone has an identity. Now we could move to second component. So connectivity. Connectivity is essentially allowing objects and subjects to interact with each other. Back in the day, connectivity was almost invisible because everything happened inside of a single computer, but you still establishing connection. Like opening a file is a connectivity, and then you using that file handle to read and write information into that file. So now instead of file handles, we're using socket handles. So everything happens over the network. So connectivity is now more important. This is where that zero trust component comes from. That zero trust essentially says that only subjects with identities are allowed to speak to other subjects or to access objects. So that's the second component, connectivity. Again, authentication, that's the first one. Second is connectivity. So once everyone is connected, and now once everyone has an identity, and I will keep repeating, when everyone and everything, so then it comes down to authorization. What are you allowed to do? So you do have access to this object. Can you delete it? Can you modify it? So what kind of access you actually have? So that's kind of authorization, the third component. And finally, audit, what is going on? On your computer, you can actually request a list of all open file handles, and you will see I have these applications that are accessing these particular files. Well, can you do it across your entire AWS account right now? Most people probably say no. Like, that's actually what's broken, what we're trying to fix. That's like an audit. Like audit and visibility, like there are two sides to it. Real time, like show me what's going on, just like I just explained. And also historical, like what happened before. So wouldn't it be nice if you, like let's just say you're operating massive fleet of servers and you pick like a random box and you pick a random file and can you answer the question where it came from? Who created that file and why it was done? So if you had like a Multics-like system controlling your entire cloud infrastructure, you would have been able to say that, hey, Ev Kontsevoy was doing a deployment 3 months ago, and as part of the deployment, he ran that script, and that script pulled this file out of GitHub and put it here. So that kind of visibility today is actually missing at most organizations, so that needs to be built. Now, I can go back to just like give you a compressed answer to your question.
Yeah.
Connectivity, authentication, authorization, audit. And that's what the book is about. So it explores like different approaches to implement those four, and obviously it suggests like what is kind of industry best practices for connectivity, authentication, authorization, and audit.
And I think you kind of touched on this briefly, but in the book you mentioned the concept of systems that have been created in the past, which have kind of solved these problems before, one being Multics.
Yeah.
For people who aren't familiar, can you describe what Multics is and what problems it went out to solve?
First of all, like at Teleport, we're great admirers at Multics. Like people who created, like the Sasha, our CTO and co-founder, when he was original, like that's where his inspiration is coming from. And it's based on like really humble realization that like most great ideas, they've been done before. Like the industry, like we're all evolving on a spiral. So in the past, when all of computing was happening within a single box, and we had the idea of operating system that kind of managed everything, but then we moved forward in time into the present, and now we're operating with hundreds of thousands and millions of machines. So we lost a lot of luxuries that operating systems used to provide. Like scheduling, for example. Like in an operating system, you just give it a process, and the process will be executed with other processes, and operating system will manage resources. But eventually, we figured out how to take this capability into the cloud. So now I have systems like Kubernetes. And access control sub-system of an OS, it's one of the things that we lost. And just like what Kubernetes is doing with scheduling, is bringing the concept of scheduling from a single box operating system to a data center scale. Like that's the vision of Teleport, to take the access control idea from an operating system and scale it up to a data center scale. Maybe like right now we're just focusing on organizations. Like we want our customers, when they reason about their infrastructure, we want them to actually now start to rely on the fact that you do have functioning access control. But it would be kind of cool to scale it up to like internet scale, where nothing is ever anonymous. Because even if you solve all of this CIA triad problems for your infrastructure using Teleport, you don't want to live on an island. You will have a bunch of microservices that are calling APIs that you purchased from other companies, from companies like Mailgun, Twilio, AWS, list goes on. You now have exact same access silo problem, but now it exists across organizations. So if I'm thinking about kind of distant future for Teleport, I'm thinking how we can solve that. So if that becomes a reality, then you will end up in an access control system that covers the entire internet. But I think I'm digressing now. Multics. I can talk about Multics for hours. Because it was actually the most advanced. It's really old, but it's the most advanced operating system ever designed. It was so advanced that most people agreed it's too complex. So Linux borrowed some ideas from Multics. Windows borrowed some ideas from Multics. But all present-day operating systems that are kind of less powerful. So for example, when Department of Defense decided to look into using Linux in production, they realized like, oh, it doesn't actually have like robust access control system that Multics used to have. And that's where I see Linux came from, because they like, oh, we need to go and borrow like more concepts from Multics simply because we do want a system to be trustworthy. That kind of reminds me of something. Like I saw the title of this podcast was like the Orange Book was in there. So if we want our systems to be trustworthy, how do we know if they're trustworthy? So we came up with this idea of like CIA triad. When I say we, I mean like computer community. Like it's not us. It came from like way back. And everyone knows about the CIA triad, but it's not as simple to evaluate, to take a look at a computer and say, yeah, this computer has confidentiality. Yes, this one has integrity. Like this system is like available. So the Department of Defense, they published this book called think like criteria for evaluating trustworthiness of a computing system, like really, really long word. But it was famously known for being the Orange Book. So if you guys saw the movie, actually like a bunch of movies about hackers, the Orange Book is in them. It's basically kind of like a manual how to protect computing systems, and the hackers would read that book to figure out how to hack into them. And the exercise that I think would be kind of fun for most of you to do is to go find a copy of this book. It's pretty hard because I think the latest edition was published in like 1976. But the book goes in great detail. It will force you to ask questions about your environments, computing environments, because your computer environments are computers. They're modern computers that we all use. And that book is also it's reminding all of us, like why we even exist, like cybersecurity professionals or security engineers, that we're in the business of making our computers trustworthy. And there is a manual that was written a long time ago by really, really smart people that basically tells you what you need to do. And in fact, you could even look at that book as a teleport long-term roadmap.
And I think one thing in Multics that we've not touched on is the concept of the reference monitor.
So in the access control theory, you have to have one central point where your policy is evaluated and enforced. In Multics, that component was called reference monitor, which means that every time you want to establish a connection, and again, connections exist even within a single computer. So every time there are two subjects, they want to talk to each other, or if one subject talks to another object, all of these connections get routed through a reference monitor. A reference monitor looks at everyone's identity, so nothing and nobody is allowed to be anonymous. And then it's going to check the policy in a segment where the subject, or where the object lives, like whether that interaction is allowed. And even though people look around now and say, hey, we have this new idea of zero trust, let's go and become zero trust organizations, let's implement zero trust architecture. But I like to point out, look, it's not a new idea. It was built in Multics many, many years ago. And now we just collectively as an industry, picking yet another good idea from the past, and we're trying to scale it up and move it into the future. So essentially, zero trust says that in your organization, you need to have a reference monitor. It's something, you could call it a proxy if you want to get really technical, but there are probably other technical ways to implement it. But there is something that basically looks at every connection trying to be established, and it makes sure that, first of all, you're authenticated. Secondly, that's going to be an encrypted connection. And finally, you could even check things what kind of encryption that is. And you could do things that's, for example, a teleport implementation of zero trust. Sometimes you want to establish connectivity into computing systems that are behind firewalls, they're not directly reachable. So you could do things like reverse tunnels. That's what teleport allows you to do, which allows you to expand the reference monitor implementation outside of a single network. But I think we're getting too technical for the purposes of a general purpose security podcast.
So can you really explain what identity means? As myself, Ev, Ben, we have my driving license. It's a form of identity. What are some of the forms of identity that's important for humans and machines?
I was always unhappy with this term that people would say sometimes, my identity got stolen, or your identity can be stolen online. And technically it's not true. Your identity cannot be stolen because your identity is stored in a physical world. To steal your identity, Ben, I technically need to steal you because if it's not you, that's not really your identity. It's something else. And the early problem with identities that we had was, and we still have, is that we apply the term identity to what essentially is an alias. Let's just say you sign up for, a Gmail account, and it asks you to pick a username and then a password. And we say the combination of those things that's your identity now. Well, that's not true. That's just an electronic record. That's just an alias that exists in one system. That indeed can be stolen. So if I look over your shoulder and I see what kind of password you picked and I see your email and username, okay, I stole your identity. Even though technically, again, it's not true. So how do you implement true identity? And that's the term we actually used in the book, just to differentiate between traditional understanding of identity and the true identity. So we kept saying true identity over and over. So true identity is based on physical properties of something or someone that you try to identify. So in the case of you, it's your biometrics, it's your fingerprint, it's things it's things you have. So all of that collectively represents Ben or Ev. And in terms of a machine, you also need kind of same kind of physical proof that that's a real identity. So as most of you know, like servers, for example, they have hardware security modules, HSMs, they live on the motherboard. So that device is absolutely unique. There is no other physical object in the world that is similar. You cannot download it, you cannot upload HSM. It's glued or soldered to your motherboard. So that's the true identity of that machine. And that is the difference that book introduces really, really early, where we talk about the importance of establishing these true identities. And establishing identities is a two-step process. Let's just use humans as an example. Let's just say that you come to Teleport, you want to get a job here. So you go through an interview, then, okay, you hired, we give you a job offer, you show up for work for the first time. The first thing, the step is called identity proofing. So you actually need to show up in person. So you probably go to something like HR department. And this is where your identity is validated. And this is where you could actually say that this is me, this is my fingerprint, we're going to give you a laptop, that we're going to register you in the system. So the important point here is that kind of verification, the initial identity proofing step, it happens in person. You cannot do it any other way. And then you need to find a way to electronically, in the future, to reference true identity of Ben, or Ev in this case. How do you do it with hardware, for example? Well, let's just say that for you, Ben, to start working in Teleport, we're going to give you a company-issued laptop made by Apple. So laptops, on their motherboards, they have a device called TPM, a trusted platform module, which is, you can think about it as a lightweight lightweight version of HSM. There's actually a blog post we wrote about differences between HSM and TPM. You can go check it out. So when laptop shows up, so it also needs to enroll into Teleport organization or your organization. And to do it, it needs to present, I have my TPM. So in Teleport, in the product of Teleport, we have this component called device ID, where you need to enroll each laptop individually. And then what you do, you link Ben's biometrics, your fingerprint in this case, using Touch ID. You could pair it to a TPM on a laptop. And now collectively, that is the identity that we could use to do trusted computing at Teleport. And the difference between true identity, which is what I just described, and the kind of fake alias identity, is the true identity is not data. I want you to think about it. A true identity is not data. Because it's not data, you cannot steal it. You cannot download or upload a TPM. You cannot upload or download a fingerprint. So that information is stored in a physical world, and that is what it makes it secure. And that's why we call it a true identity. So for those of you who don't know how this kind of pairing of fingerprint to TPM works, because sometimes even engineers ask me these questions well, isn't this annoying, or it violates my privacy, they would say, when I need to contribute my fingerprint to a company. But that's not actually how it works. When you enroll your fingerprint, when you're using Teleport, for example, your fingerprint doesn't leave your computer. It doesn't go on a wire into any kind of server. Instead, your fingerprint basically gets stored on a TPM, and it's the hardware itself that does all of this. It's unhackable, at least that's what hardware manufacturers are telling us. So which means your fingerprint, the signature of the finger, gets stored and signed by TPM itself. So that's really what creates this kind of physical, true, real-world identity that is not exposed as data to any kind of software. So again, cannot be cloned, cannot be downloaded, cannot be uploaded, cannot be sold on a darknet by a bad Apple employee. That's what true identity is, and it's kind of foundation, you start building the rest of your access control system once you have that foundation.
Cool. So going on from your recruiting example, so I've come in, got fingerprints, got my laptop, all enrolled. The next stage is connecting to whatever I have. And I know you talk to lots of people. What are some anti-patterns you see around connectivity, things that people are doing wrong that they shouldn't be doing?
So you're essentially asking me to overgeneralize and then criticize a bunch of people I've never met and just acquire a bunch of enemies. So the one thing that I personally never quite subscribe to is, some people call it defense in depth. Some people call it kind of security through obscurity, but trying to hide SSH port that a particular computing system responds to and putting it on a less kind of common port. When we do that, what do we actually say? It just means that we're not trusting like our own like access control system, so we don't even like want people to connect to it. So that's one thing that I find a little bit silly. I personally run my own like home, let's call it a small data center. Like I used to have half a rack in the data center, but now I just have my basement. And all of this is kind of open to the world on the port where it's supposed to respond. And it's just because I use a connectivity solution or trusted monitor, reference monitor that is truly trusted. Another anti-pattern that is actually really, really common, unfortunately, is like basically use of shared credentials or shared identities. So this comes from like a very simple realization that, okay, my infrastructure is complicated. I have, and I in this case is like hypothetical cybersecurity engineer or DevOps engineer. So I have 100 plus different technologies in my environment. Now, every single one of them, I don't know, like it could be Kubernetes, a database, some kind of CI/CD system, some kind of dashboard. There are lots and lots of DevOps tools and technology solutions that we all have to run in our clouds. And they all have like a config file and a documentation that says how to like configure TLS for this thing. And there's like 100 plus of those. So now my DevOps team needs to figure out how to configure like authenticated connectivity into every little thing. And that is just like time consuming. And sometimes people, frankly, just don't even have the expertise. And because look, we all know how horrible documentation could be. Like with some of these things, it's really challenging to figure this out. So then people just at some point, like, you know what, we're just going to create like, I don't know, like a VPC, some kind of private network. And we're going to have this like one credential or two or three credentials for kind of different roles. And instead of going through the pain and configuring every single tiny thing, we're just going to set up the perimeter and we're just going to, that's really where all the enforcement is going to happen. And obviously that's like anti-zero trust, because in this case, if that particular thing is compromised, then someone kind of breaks through the perimeter. So the blast radius will be kind of equal the size of the perimeter. And that's actually what you see in the movies too, like in the Matrix or whatever. They always say like, oh, like hackers penetrated the network. So like you hear that, that's anti-pattern. Like in fact, hackers should be totally allowed in the network. The one system that I frequently use as a very common example of a true zero trust implementation is your phone. Your phone is a computer. It's equivalent to a server, like EC2 instance in your AWS account. I would say it's more powerful than some EC2 instances, and it could have been the most powerful EC2 instance, I don't know, like 10, 15 years ago. And now think about what happens from Apple perspective. So you have like 1 billion plus iPhones in the world. That's a cloud environment, don't you think? Like you have a bunch of servers like somewhere out there, and you're running an application called iOS on every single one. Then you have a new version of iOS, and you need to push it to these phones. How is that different from a cloud deployment? Like we all do deployments like every day. And now notice the interesting thing, like Apple runs this system without network protection. Every phone is on a public internet. There is no VPC. There is no firewall. There is no tracing, monitoring. Actually, most DevOps tools are completely absent. And it's actually incredibly resilient. And also, like every server is managed by extremely incompetent engineer. Let's put it this way. And it's fine. Like, has anyone ever heard about an example, someone hacking into an iPhone through an iOS update mechanism? This is zero trust. It's a zero trust fully implemented. The way it works, your phone has a TPM, so it's not hackable. It only trusts Apple, so it's not zero trust. It's only trust Apple kind of trust. It establishes a reverse tunnel into Apple data centers, and then it gets updates through that tunnel. So even though you ask me about anti-patterns, I would rather say that everything that's not this is an anti-pattern. So that's how I think organizations need to think about designing their infrastructure. So then like one day they could just open up the VPC or firewall and just imagine that every device you have on your AWS account or in your data center has a public IP address with no firewall protection. And if you feel as competent and confident as Apple, that means you achieved a true zero trust.
Yeah, going on a bit of a segue, and this is a great introduction plug for Teleport. Now's your time to introduce it. So for people who are listening who've never heard of Teleport, could you just give a quick introduction about why you started Teleport the company, what the Teleport product is?
So first, let me introduce Teleport. So Teleport is an access control system or what we instead now say that we're open access platform for your entire infrastructure. And the goal is to give you like a practical way. And when I say give you, like it actually applies to everybody because Teleport is open source. This is why we say we are open source platform, is to give you a very quick and operational and a tangible, very practical way to implement access. Like from a connectivity perspective, it's really similar to like the iPhone, cloud of iPhones examples, but it also tries to deliver all of best access control capabilities of Multics into the present that is cloud native and it's compatible with modern kind of DevOpsy way of doing things. So Teleport is access control for a cloud from kind of Multics perspective. Now about the history of the company, how it all started. It was somewhat similar to a history of Slack. Because Slack started as a gaming company, right?
Yeah.
And a Slack was an internal tool they built for chat. Similarly, Teleport, like the legal name of a company is actually Gravitational, where we wanted to, maybe it would be kind of ambitious thing to say, but we wanted to build a Multics-like system in the beginning. Something that allows you to build a software, package it, and easily distribute it anywhere in the world, and it would run by itself, just like iPhone software, without DevOps teams, hopefully like for years. That system was called Gravity, and the company was named Gravitational after that. Gravity did have customers. The use cases were like, how do we deploy applications? Like, for example, think of like a fast food restaurant chain where you have 50,000 locations, and every location has some servers in the back. So how do you build a deploy application that works in a scenario like this? So you need something that allows you to have like thousands of replicas of exact same software running all over the world. This is, again, where analogies with iPhone come from. Or if you think about autonomous driving or autonomous flying platforms, some of those run Kubernetes on every single unit, believe it or not. So how do you build applications that you could deploy and run at this scale, where you have, again, thousands and thousands of Kubernetes clusters and instances? And we were trying, when we were building Gravity, problem number one, I'm a C programmer, I should say program number 0, was that we needed access control system that would allow us actually to make this overall network trustworthy. So it all goes back into this trustworthiness. And Teleport was built as an access control subcomponent of Gravity. So if you think of kind of Gravity as kind of loose analogy to Multics, then Teleport is the reference monitor that was borrowed from Multics. Needless to say that Gravity, it did okay commercially. We had some really like large customers, and it's actually still, like we donated Gravity to other companies. It's now open source. You can find it on GitHub. But needless to say that Teleport, once it became available, it was also happened around the time of COVID hit, where a lot of organizations started to rethink how access is implemented and enforced for their infrastructure. And the rest is history. So Teleport became really popular, and all of you discovered it. So thank you for coming. And now I guess it's a success story.
And you might have mentioned this briefly, but Teleport's an open source, open core company. Can you sort of describe why open source is important to Teleport?
The way it was open sourced, it was almost accidental. At the moment, we haven't thought about this much. We wanted to hire best engineers available worldwide, and engineers, they enjoy working on open source software. So that was maybe a original reason, because we wanted like the most ambitious engineers to join the company. But also, the founders of Teleport, we actually did not come from classic, traditional cybersecurity background. We came from infrastructure background. Teleport was founded by cloud founders. And for that reason, we were always, like, let's just say, like, we were extremely careful, almost conservative on all things security. And we saw open source as additional check on a company. I remember in the early days, I think it was either all of Teleport or something about Teleport got posted on Hacker News. And I remember all these programmers who frequently go to that website, they started dissecting Teleport source code line by line, arguing between each other, is it secure or not? And it felt a little bit terrifying, because like people are examining the result of your work. But when they collectively agreed that that was the most secure way to get something done, the feeling was extremely reassuring. So that is probably the most important reason I can think of why we decided to stick to open source model, because it keeps us honest It elevates the bar because I think any engineer, when they know that after typing git push, 8 billion people will see what you just done, even though, of course, they're not going to look at it right away, but I think it makes all of us to think twice about code we write, about our designs. But it also invites other companies and the community to participate in that process. So the value of being open is not just because your code is available. It is also extremely important to be collaborative. So if you look at, like most projects you're hearing about today, like we're talking about machine ID and identity security, governance, and teleport access graph. Look, all of these things have design documents. And you could see them on GitHub, and you could see discussions, and you could see extremely smart people who work at the best cybersecurity teams in the industry participate. So it allows us to actually build teleport in the open. So we believe that having thousands of eyes looking at what we're doing, I guess this is how we deal with our realization that you cannot be the smartest person in the world, but you do want to build the smartest product in the world. So that's, I think, why we're open source. It also builds trust, I believe. Like in the opening keynote, there was this, even though it was about management teams, like the trust is a foundation of everything, and then the transparency was right there. So because those two go hand in hand. So we are open source because we want to build trust with our customers, users, and a broader community.
So going a little bit back to the pillars of access, we talked a little bit about authorization, and we both worked at a very large hosting provider back in the day, and we saw some interesting patterns around access to resources, both from support and engineers, and some interesting organizational complexity around those. What are some patterns that you've seen that have worked well, that have given engineers and teams the right amount of access to their systems?
My view on authorization, that it's still broken. Today, what day today? October 25th, 2023, authorization is broken. So here's why it's broken. So imagine a table in a MySQL database, or Oracle database, or SQL Server, pick your favorite. Now, can you confidently tell me a list of people who could delete entries in that table on 2 p.m. tomorrow? Just think about it. Like, is that a hard question to answer? Is it an easy question to answer? And then if you can produce the answer, how confident are you that that's true? And here's why it's really, really hard. So let's just say you can go into that database and you could examine different roles and permissions for users that exist in that database. But the scope of those users is limited just to that database, which means that even if you configured RBAC properly, I could go through SSH into that box, and I could do SQL dump. I could take it out. I could modify that table, and then I could do insert it back. And none of this will be detected by authorization engine of a database, because I've done it using completely different pathway. But it's not just SSH versus database, because if you're running that database in a Kubernetes, I could get into that pod using Kubernetes API. And if you're doing it in the cloud, I could do EBS volume dump using EC2 API. I could use AWS console. You see, all of these things, they also have authentication, they have users, they have passwords and whatnot, but authorization engines are different everywhere. How common it is for organizations to be so well organized that the role-based access control rules are fully synchronized across all these different layers of technology. And by the way, there are more layers that I could have mentioned. And the thing is, almost no one does this today. So that's why we believe that authorization is broken. So authorization today is extremely siloed. Here's another example. You could think almost every company wants to implement a rule that says developers must never read production data. Kind of makes sense. You don't want random Googler to read your Gmail. Okay, now think about what it actually means to implement that rule. How many different authorization engines and how many different layers of your technology stack you need to go and update properly for that rule to be enforced. I consider this to be the next biggest problem we need to solve with authorization. We could say that for authentication, we almost solved this problem by introducing SSO. You have single sign-on that allows you to log in once, and then you have access to a bunch of systems. And now look at Okta. It's a huge, successful company because they're an SSO provider. My question is, where is SSO for authorization? Where is it that I can go and define that I'm an intern and I should only access things and have privileges that interns are allowed in this company. We have not solved this problem today, and it's one of the biggest reasons why the frequency of those breaches goes up and up. Because effectively it means that almost every hack, the blast radius is enormous. Because we continue to run, and when I say we, I mean like all of us collectively, the industry, we continue to run a bunch of workloads that essentially are misconfigured. I'm not claiming that Teleport solved this problem. Like, we're working on it. So this research project that we've been investing into for almost 2 years now called Teleport Access Graph, like, that's our attempt at solving it. I'm hoping that we're going to start actually making pieces of it available gradually in 2024. But I invite everyone to visit a presentation by our CTO about TAG. At least you will kind of see what approach we're trying to take.
So I'm going to follow up 2 questions. I'm going to touch a little bit on audit since, it's last. It always comes, it skips the agenda. So I know CrowdStrike reported that it can take 84 minutes between a credential being leaked and a breach, which seems like a very short amount of time. What are some tips for teams to sort of get ahead of this to reduce the possibility of attacks on the infrastructure?
We obviously talked about zero trust before. So the zero trust architecture basically means that the blast radius will be hopefully contained to a single workload that got infected. So that thing alone, if you are a true zero trust company, using iPhone as an example, if one iPhone somehow got breached, maybe because I'm just going to yank it out of your hand when it's unlocked, I cannot infect other iPhones from this one. It's completely isolated. That's true. That's zero trust. Like, no iPhone trusts any other iPhone. So if your infrastructure is like that, then you largely solved this problem earlier. Which kind of brings me to, I'm about to say something really controversial that might even ruin my career someday. I believe that industry right now pays an oversized attention to visibility and audit logging. And the reason is because authorization is broken. So think about it this way. What is policy? Policy is a set of rules that need to be obeyed. They need to be true if you don't want your data to be misused. If you want your system to be trustworthy, your policy must be enforced. But you can also think of a policy as a program, code. It's a declarative programming language on some level. Now, the question is, how can you validate your policy? How can you write unit test that says that your policy is correct? And because policy today is fragmented, incredibly fragmented, and because different policy engines or authorization engines, they're not compatible with each other, and they are, let's just say, at different levels of maturity. So because your authorization is broken, a lot of cybersecurity professionals simply say, hey, I know that my infrastructure has authorization problems, so therefore I need to assume that I always have bad actors on my network, and observability is how I'm going to catch them. This is why a lot of people are investing into anomaly detection, into SIEM systems, because that's actually the last line of defense. If you couldn't prevent the bad actor from entering your infrastructure, at least you can try to catch him before 84 minutes expire. And here's my controversial take, that I believe that once we actually build a fully functioning access control system that solves this unsolved authorization problem, then the importance of observability will go down. I'm not saying it's going to be useless or obsolete, but I do think we will have a more balanced view on cybersecurity where bad actors will become an extremely rare event on your infrastructure.
Great. And just to close it out, I often like to ask the guests one just practical tip that they can deploy today or this week to secure their infrastructure.
I'm really bad at overgeneralizing, but I do want to return to this theme that at the end of the day, it's all about people. It's not hard to build a very secure system. Just cut access to everyone and everything. It will sit there completely unused. It will be super secure. But people won't be able to get anything done. And it also applies to the pattern of adopting secure technologies. I'm not sure how well known that fact is, but it's actually quite common for engineers to build backdoors into the infrastructure of companies they work at. And they're doing it on purpose. And we brag about it to each other when we go to parties. You probably all heard about it. Like, you might meet an engineer from company X and you ask him, what do you guys do for access control to your cloud, and they will say, oh, we use this vendor and that vendor, but I built a little proxy here on the side, because when the latency is up and my Cassandra is dropping packets, I don't have time to go through all this kind of official bullshit. So I have this thing that I use to kind of fix problems. It's really common. This happens because cybersecurity vendors build solutions that just get in the way and preventing people from being productive. This also happens because cybersecurity professionals who buy these solutions and set things up, they only care about this security thing in isolation from everything else. And that's the practical, I'm not sure how practical this tip is, that just put security aside for a second, and let's just all remember that we're in the business of doing computing, which is this beautiful dance of hardware, software, and people. And we are in the business of making it trustworthy. We all need to trust each other. By making things closed, hard to use, making things that get in the way, you're destroying trust. You're making engineers distrust security teams who work in the same company. We actually see it with even when we go into an organization to have conversation about using teleport over there, it's very common to feel the animosity that exists in the room between engineering and security. Because people feel that security gets in the way, prevents them from being productive. So let's just be nice to each other and not do that, and design systems to be trustworthy and nice to use.
Thank you, Ev.